All right, let's talk about these characteristics. Okay, so all the characteristics we need to answer are over here. And we need to be able to answer all of these from a picture of the derivative. To start, let's actually look at the picture of the actual function and answer the characteristics of this function from the picture of the function. Okay, just to make sure we know what we're talking about. So I've graphed the actual function is the dotted black line. So the things we need to be able to answer are, where is the relative maximum? So my relative maximum occurs right there at the top of that hill. So I'm going to say that occurs at x equals -1. Now right now we're just worried about where it happens. So I'm just going to say at x equals -1. Where is the relative minimum? So that's the bottom of this little valley, the minimum, the low point. So the relative minimum is at x equals 2. Intervals of increase. So remember, increasing functions as I move from the left to the right are going up. So these green sections would be my intervals of increase. So I would say -infinity all the way to -1. And then I would also say 2 all the way to infinity. So that would be my interval of increase. Interval of decrease is going to be what's left. Now that's going to be this blue section. So that's my interval of decrease. So that's going to be -1 all the way to 2. Okay, so that's all review. So technically all of that is from our coordinate algebra class. All right, so the last question is asking about concavity. So that's the first new concept. So concavity, if I actually have the picture, is all about concave up and concave down. Okay, so it's going to change around here. We'll talk about how we decide where that point is in a minute. But the thing is concave up. The function is concave up where it looks like a cup. Imagine if I poured water from above, it's going to hold it. So that blue section is concave up. So that's going to be from -1/2, and we'll talk about that later, how I got that, to infinity. We're just approximating for now. Concave down is like a frown. It's like an umbrella. So this green section is concave down. So this function is concave down from -infinity all the way to -1/2. Okay, so my point of inflection, that's where I change concavity. Inflect means to change, so something has to be changing there. So I'm changing from concave down to concave up. So that occurs at x equals 1/2. So that's what these things actually mean if I could actually see the original function. The problem is, I normally can't see the original function, okay? I really never can on a test. So all I have to work with is the derivative. So I've graphed the derivative in red of the original function, so it's graphed in red. So all I can actually see is that red curve. So I need to focus and base all my decisions off of that red curve right now. And I need to answer all these same questions, but instead of answering them from the graph f of x, I need to answer them from the graph of the derivative. Okay, and I'm going to leave the actual function so that I can kind of compare and see that it's actually working as I do this. So the first thing I want to look at is actually I want to skip down to intervals of increase. So our intervals of increase, so we said this thing was increasing from -infinity to -1, so that was here, okay, and then here. So that's where my function was increasing. So what I want to do is I want to look at my derivative and see what is the derivative doing on those domains. So if I look at this kind of derivative, that's the thing in red, it seems like my derivative is always positive, okay? So it's always above the x-axis. So if the derivative is positive, the function is increasing. So if the derivative is positive, the function is increasing. So how would I answer intervals of increase? So it'd be the same reason, or the same locations. So these aren't going to change. But my reasoning is going to be because f prime of x is positive. Okay, f prime of x being positive means f of x is increasing, which is the thing I'm looking for. Where is it increasing? Okay, the interval of decrease. So if I look at my original again, so where was this function? The original function was decreasing here. Well, what do I see my derivative is doing? Well, the derivative is always below that x-axis. So I can see that the interval of decrease is still -1 to 2. And my reason is the derivative is negative. Okay, so the derivative being negative means the function is decreasing. So there's my justifications. So now we'll talk about relative max and relative min. These can be done from a graph. Okay, it also, if you had been presented a function, this is where you would have to make a first derivative chart. All right, but I'm working from a graph right now. So the question is, where is there a relative max? Well, what I see is the relative max was here. So let's look at the derivative and see, what is my derivative doing? Well, it looks like the derivative is changing from positive to negative down below that x-axis. So the derivative changes from positive to negative, which means the function changes from increasing to decreasing. And if I think about a function going up and then a function going down, that makes sense that that's a maximum. So the maximum occurs at the same place at x equals -1, but my reason based on the derivative is because f prime of x changes from positive to negative. Kind of running out of room. So relative min, I'm looking for kind of the same things. So relative minimum, so I can see that it's right here. So let's look at the derivative. So with the relative minimum, the derivative went from negative to positive, because the derivative being negative means the function is decreasing. The derivative being positive means the function is increasing. So my relative minimum is at x equals 2 again. I'll save some room by not writing it. And the reason is because the derivative changes from negative to positive. Okay, so all of our justifications have to be talking about the derivative, not about the function, not about the second derivative, about the first derivative. All right, the new things, this idea of concavity. So I'm being presented a derivative graph, and I want to know, where is my function concave up? So if I look at the concave up, that was this blue graph again. So that's where this thing is concave up. Well, if I analyze the derivative on this domain, we see that the derivative is always increasing. Okay, so that's what I'm looking for. So if I'm trying to decide where is my function concave up, what I need to look for is, where is my derivative increasing? So the answer will be the same place, but my justification now is that the derivative is increasing on those domains. The definition of concave up is that the fact that the derivative is increasing, period. So where is it concave down? Well, it's the opposite. So my function is concave down, down like a frown, right here. That's concave down. So I need to look at my derivative. What is my derivative doing on those areas? Well, I can see that derivative is decreasing. So my answer is the same, but my reasoning is that the derivative is decreasing on those domains. And the very last thing is the point of inflection. Now, point of inflection means change. So to inflect is to change. So my justification for inflection, my justification for change has to be a change. I can't say it's a change because this equals 0, because that's not a change. That's a stated fact. If I told you, hey, I'm going to change, I have to tell you this is what I was before and this is what I'm going to be after. There's actually a change in behavior. So the point of inflection implies a changing in inflection. So a changing in concavity. So I can see that that inflection point is right there. If you look carefully at the scale of the graph, it's at 1/2. So if I look at what the derivative is doing right there, I can see that the derivative is going from decreasing, which would imply concave down, to increasing, which would imply concave up. So the concavity is changing. And the reason the concavity is changing is because the derivative is changing directions. Because derivative increasing is concave up, derivative decreasing is concave down. So a change in concavity implies a change in direction based off of the derivative. These are the only ways